Welcome everyone again to another episode of the ideaXme show that profiles the humans behind the big ideas that are shaping our world, inspiring the future and future creators, and for all those that like really great stories. I'm Ira Pastor, your life sciences ambassador along for this journey. So as those that listen to the show know, we've been spending a lot of time on different topics pertaining to human health, disease, degeneration, focusing on a lot of the different therapeutic and preventative interventions being developed in the private sector of the economy. And we've also had representatives on the show from various independent agencies of the United States federal government to discuss many of the exciting public sector discoveries and developments that are occurring that ultimately possess a massive, we'll say, trickle-down effect to benefits of the United States general public. In recent months, we've had a few guests on from the National Aeronautics and Space Administration, or NASA, that are talking about various topics on how science up there ultimately helps improve the life down here for us in terms of the biodynamics of suborbital spaceflight or isolation training and preparing for the mission to Mars. Today, we're going to go down another very fascinating related path as we are joined by an expert thought leader from the Defense Advanced Research Projects Agency, otherwise known as DARPA, which is an agency of the United States Department of Defense that is responsible for a variety of emerging technologies for use by the military with a mission to make various investments in breakthrough technologies for national security. Originally known as the Advanced Research Projects Agency, or ARPA, the agency was created back in 1958 by then President Dwight Eisenhower in response to the Soviet Sputnik launching, and ultimately by collaborating with academia, industry, various other government partners, DARPA has this mission to formulate and execute research and development projects to expand the frontiers of science and technology, often beyond the immediate needs of the United States military. Joining us for this fascinating show is Dr. Eric Van Giesen. He's a program manager in the Biologic Technologies Office at DARPA. Dr. Van Giesen received his bachelor's in chemical engineering and PhD in biomedical engineering from the University of Virginia and joined DARPA as a program manager in 2017 with the goal of using host-based methods to mitigate the impact of emerging disease threats. He also explores various epigenetic and real-time monitoring approaches to dynamically guide healthcare decisions and therapy, and develops new methods of increasing patient survival in austere environments using various intelligence systems partnered with local care providers. Throughout his career, Dr. Van Giesen has worked with both private and interagency government partners to build diagnostic and healthcare solutions. One core example being a very novel patient transport system known as the Containerized Containment system, which was a platform that received an R&D 100 award and is currently in use by the Department of State and the Department of Health and Human Services. He also created a university-based drug development pipeline to accelerate development of therapeutic products for guarding against weapons of mass destruction and emerging disease threats. His work has led to various technologies that link home use and point-of-care diagnostics with health surveillance capabilities, especially in resource-limited environments with the goal of stopping epidemics before they even emerge. Dr. Van Giesen has led the technology development evaluation efforts and diagnostics for the Department of Defense and supported major diagnostic acquisitions and science and tech programs. He's published extensively on a range of topics from genomic analysis to autonomous systems. He served as the chief judge on the Nokia Sensing X Challenge, as then a judge in the Qualcomm Tricorder X Challenge on behalf of the X Prize Foundation. And most recently, very exciting, in real time, described as a potential game changer, he and his team are right now waiting for FDA emergency use approval for a fascinating new diagnostic, originally developed by, to diagnose people poisoned by chemical warfare, which may be able to detect the presence of COVID-19 virus as early as 24 hours after a person is infected, so weeks before they become infectious. Really exciting new concept to fill a major diagnostic gap. All that being said, Dr. Van Giesen, thank you for taking the time out of your schedule, especially on Memorial Day, for joining us on the show to talk for us a little while.
Well, thank you for having me. Very exciting.
Yeah, it's a real pleasure. To get started, we typically give our guests the floor for a little bit just to talk about themselves. If you can, just for a few minutes, tell us about yourselves, or where you grew up, how you got interested in chemical and biological engineering, and a little bit of your path to joining DARPA in 2017. That'd be awesome.
Absolutely. Yeah. Thank you very much. Well, I mean, my background, starts, with DARPA anyway. It starts at a very early age. I've been fascinated with the agency, even reading about it in magazines as I was growing up. And I've also had friends and even family. My father-in-law was a former, leader at DARPA. And so I learned about the agency as I was kind of coming through my career. And there was always something in the back of my mind that said I would love to be able to work in a place where you can come in and solve major problems, and have a group of colleagues that could work with you to refine your ideas, and then also you could work with the best people in the world to create these solutions. Right at DARPA, what's amazing is you have this freedom to engage essentially the entire global scientific and technology development community when you want to solve a problem. And if it's going to be solvable, that's the way you want to do it, right? You want to have the best people working on it, and you want to be surrounded by the best people, so that as you're refining this idea, they're asking hard questions. They're making sure that what you're thinking about and the approach you're taking has been essentially refined to a point where it is achieving that balance of feasibility and innovation, right? And that's a critical thing. As you're building something at DARPA, there is this idea, I think, out in the rest of the world that, people just come in here with crazy ideas and they stick them up against the wall and they hope they work. And that is not at all how it works. We are always on this knife edge of, do we think it is possible, and what's new about it, right? That is a very difficult tightrope to walk. And that is what we're trying to do at all times. So you have to find evidence in the world that what you're thinking about is doable. So I think that it's been a wonderful opportunity. As I've been developing through my career, there were always points in time where I thought maybe I should come to DARPA now. But I actually, I had one opportunity about 10 years ago that I realized, I think I need more time. I need more time to develop and be ready for this. And finally, in 2017, the time was right. I felt, in terms of the confluence of, what I had learned throughout my career, but also the number of, people that I knew in the scientific community. I felt that there was a very unique point in time where I could take advantage of all of that to build new ideas at DARPA. And of course, as you know, like, my quest has been from the beginning to change how we think about diagnostics, right? And that is really what I came in doing, right? You're supposed to come into DARPA with your hair on fire. I don't have a lot of hair to get on fire, but I also have a burning desire to get something done. And when you come into DARPA as a program manager, you get 5 years, and then they ask you to move on and let other people come in with new ideas. And that's exactly you have to take that 5 years and go full throttle and make sure that whatever you are hoping to do gets done. And if you don't have a burning desire to get something done, wait until you do before you come to DARPA.
Wonderful. Yeah, I mean, as an outsider, I was telling you offline, I spent most of my time in sort of the traditional pharmaceutical industry. And, back in the day, there was always sort of this group on the side. It didn't have the resources of oncology or neurology or cardiology, but it was set up where some scientists could explore things that were sort of outside of the scope of the traditional drug development business. We don't really see them doing this too much anymore, but it's sort of, DARPA always struck me as sort of a place like that. There's, you're part of the defense department, but you are allowed to think outside of the box, think of really creative things. Along those lines, could you sort of, using you have this fascinating containerized biocontainment system that you developed, this really sophisticated isolation system for people that are maybe in difficult environments that need to be transported elsewhere. You've worked on it, but also brought it in the private sector, the Paul Allen Foundation and so forth. Can you talk a little bit about how sort of the process typically works. So usually, I'll read something on the internet about, wow, there's this new DARPA proposal out there for something really cool. But then sort of what happens next? If you can walk us through that a little bit, that'd be great.
Well, I'd have to detangle two different things. So the containerized biocontainment system was obviously before I got to DARPA. That was built in response to the 2014 Ebola outbreak. And the State Department and Paul Allen Foundation had come together really in a really unique public-private partnership. A gentleman named Dr. William Walters, who is the head of operational medicine at the State Department, was the one who facilitated that amazing alignment between the private sector, an NGO and a government agency to allow for us to be creative and build an innovation. And actually that was a really inspirational point in my life. As of 2014, it was something that allowed me to realize that if we put enough, positive design momentum behind a new idea, we can make it work, right? And we can do it against convention. We don't have to follow traditional funding mechanisms or traditional idea pathways. And so essentially we got in a room and put that thing together on a whiteboard and a napkin. My company and the State Department and some people from Paul Allen Foundation, and we decided this is something we have to do. It was done in about 90 days, but it was one of the fastest turn engineering projects that I've ever been on of that complexity. I would still say it was one of the best engineering projects I've ever done. We had a team of engineers at MRI Global who were just absolutely spectacular, but we also had amazing people on the government side giving us the tools and the resources we needed to actually get this done. And we continued to refine that system even after the Ebola outbreak through a series of tests where we utilized 747s and military aircraft to make sure that this system was ready for this outbreak. And it has had a major impact on transport operations. They use the system in the Diamond Princess evacuation, and they've used it in many other evacuations you haven't heard about. And it's really a testament to the preparation and the foresight of another government agency that actually should restore the faith in all of us that there are creative people and exciting people all over the government that are willing to kind of work within the limits of the government acquisition rules to make really innovation happen or innovative things happen. But then going to DARPA, I can tell you a little bit about the process. Sure. And there's actually a relationship between these two spaces, right? I mean, what we did in the CBCS was kind of a rapid turn innovation, and it was unconventional. But we went through the same process, and the gestation of a program at DARPA, it follows a very similar path, although it takes a little bit. It's actually a little bit of a longer time frame than what we did in the CBCS. In the CBCS, we did almost the same things. The first things we asked were, well, what new thing can we do, and how is it possible? What is the realm of the possible, the feasible? And then we essentially refined. I mean, we started all kinds of different ideas, probably 30 different ideas, and went down to something we thought was actually doable. In DARPA, you're doing a similar thing when you're forming a program. You're sitting down with a team of people. There's a whole science and engineering technical support staff that works with a program manager, and their job is as significant as the program managers. But you're also working with your leadership. Your leadership, all the way up to the director of the agency, is aware of this new idea, and they're all working with you and asking the difficult questions. And you are working at the beginning, before you even are quote unquote pitching the program. You're working and socializing this idea and refining it to explore all the options in terms of the art of the possible. You're amassing massive amounts of literature, very similar to what you might do as you're building a dissertation concept, and similar quantities of literature are being amassed. And you're reading as much as you can, and then you're kind of using the whiteboard process, just like we did in CBCS. You're whittling down ideas until you find something that makes sense. And it's not like you're solving the problem, but you're developing a way in which you can frame the problem, and you're also exploring the technologies that you think can actually solve the problem. And then once you've got that point, you're answering these subtly or deceptively difficult questions called Heilmeyer questions. George Heilmeyer was a director of the agency back in the 70s,
Okay.
and he constructed these questions. And it's really a gauntlet to put your program idea through. And you're answering these questions in a way that satisfies all of the potential stakeholders in not only the agency, but also the end user community, the people in the military, and the other parts of the government that might benefit from this technology that you're developing. So you're working very hard to refine the idea so that it creates a satisfactory set of answers to the Heilmeyer questions. And some people take years to do this, to build a program. And it's not really a highly, I guess, publicized process, but it is essential to any program to be formed. You have to get through and adequately answer these Heilmeyer questions.
Mm-hmm.
And it might only be a 3-page document, but you took maybe, anywhere from 6 months to 2 years to formulate the right answers to those questions. The product looks simple and you say, oh, of course, that was easy. And no, it wasn't. And then beyond that, you're working hard. Then once you've satisfactorily answered those questions, you're building a presentation and you're building a set of supporting documents, program description documents. And these are all going forth towards, you getting the program approved by leadership. And you're
Mm-hmm.
you essentially go in front of a council of leaders in DARPA, all of the office directors and all of the other people who are, sitting, in other offices and may not be fully aware of your program. And these people are all sitting there reviewing your proposal in real time in a presentation that lasts about an hour. And that can either give you a thumbs up or a thumbs down in terms of moving forward on the program. If you get the thumbs up there, then you're working to get the broad agency announcement out and begin the advertisement of your program. You're putting out press releases, you're having large group meetings, and that program then becomes, something legendary, we hope, right? That's going to change the world. But it is imperative as a program manager that you do this early in your career as a program manager. You only have 5 years. This whole process, by the time you start the program, it could be 6 months to a year. So you've already lost maybe 20% of your entire program or time there if you, as you go through and build this program. So you want to make sure it's successful and you want to work as hard as you can and as fast as you can to get it out. So that is usually what happens for all of us. And now I'm working. I've done 3 programs now. I'm probably going to do a 4th. But they've all followed a theme, and a lot of us weave together stories about our programs.
Sure.
Our programs create a narrative typically about problems we want to solve, right? Mm-hmm. And so for me, the problems I want to solve revolve around human health, and they revolve around humans responding to their environment. And then the last 2 programs I've kind of gotten into, or the last program that I've put out and one I'll be putting out is more surrounding the idea of how can I augment our own ability to respond to the environment? Mm-hmm. So the first 2 were really about understanding that response, and then the next 2 will be more about how can we refine and improve that human response to threats in the environment.
Outstanding. I appreciate that overview, and it's really I say the word ecosystem, but the way that you organize this and have the ability to tap into these resources, although obviously you mentioned the limited time, but nonetheless it's truly remarkable stuff.
Yes, I mean, just one thing to add there. I mean, you can add so much flavor, if you will, to a program at DARPA like you couldn't anywhere else. I mean, I can call the CEOs. I mean, CEOs of companies will take your call all of a sudden, and they'll take your,
like that.
They'll take the university leadership, top researchers in the world. If you call and say you're DARPA, they will answer, and it's just absolutely amazing to be able to get access to these types of individuals as you're building your ideas, and they're willing to kind of just openly speak with you about this. Nowhere else have I been where I've had that kind of access. So it's that part is it makes sure that you're getting the best answers you possibly can, and that is a good thing.
Absolutely. Let's take a little time now with a few of the projects that you have started, and obviously the most the most current one, the most prescient one, is this diagnostic that's under FDA emergency use approval right now, originally designed to look at chemical warfare poisoning. You've obviously modified and tweaked things. If you could walk a little bit through that, that'd be awesome. But at the same time, obviously I'm always thinking of the sort of your future vision for how this can help the rest of us. Obviously, you're in solving the COVID issue, you're helping all of us, but then I'm thinking for some of the press mentioned, other possibilities in terms of point of care diagnostics, remote testing of people in clinical environments and so forth. So obviously this one tool can yield a lot of other possibilities. Can you talk through some of that as well? That'd be awesome.
Absolutely. One thing to clarify, we always built this program that we're about to talk about, not just for measuring chemical agent exposure, but also to measure the exposure to infectious disease. So it was always envisioned as a diagnostic for infectious disease, in addition to exposures to other things, right?
Okay.
And it all started, from experiences I had in 2014. Again, the major Ebola outbreak of 2014 and 2015 really cemented my personal quest to build a better way to diagnose disease. It was clear that the failures that were experienced in that outbreak, which seems small compared to what we're dealing with now, but that was a major outbreak and pandemic really among many nations, right? And so that particular event made me realize that we are not doing a good enough job diagnosing disease. And unfortunately, it wasn't as obvious to the American public what was going on, but we were unable to diagnose at the point of care at the beginning of that outbreak. And when I say at the point of care, like where the care provider is meeting with the patient, that the care provider did not have a mechanism at the beginning to actually provide a diagnostic result other than classic symptomology, right? They did not have a test, a blood test or any other type of test. They had to actually take samples, and at the beginning they were waiting up to 48 hours, 72 hours for an answer back about that patient. Meanwhile, that patient was sitting in areas that with other people who had suspected infections, and some of them probably had malaria. And so those people with malaria might have ended up getting Ebola because of the proximity they were within these other people. And in fact, that did happen. So we had a very big problem in terms of making diagnostics available, but we also had a problem in terms of, especially with Ebola, the time in which you can actually detect Ebola, releasing from the body or shedding from the body, right? Viral shedding. Sure. Is limited. It's very limited in Ebola infection. And so there was this problem of people being, sick with Ebola or infected with Ebola and not having a detectable amount. And so they were not necessarily positively diagnosed when they actually had it. And that is what we call a very limited diagnostic window. And so the question I had was, how can I diagnose better? How can we look at how the body is responding to Ebola or another infection, which is a more constant thing, right? As long as we have symptoms, our body is responding somehow, right? And even afterwards, we're responding because we're making antibodies to Ebola for maybe years or decades later. Okay. And so that got me to the epigenome, right? And so this thing called the epigenome is, think of it as kind of two things. Number one, it's like a flight data recorder in your body, right? Every cell in your body has a little mini flight data recorder, a black box, if you will, that is recording every event that happens to you. It's doing that so that it can learn how to use your own genes, your own DNA to respond to the environment. And so when you're responding to an infection, what's happening is your genes are actually being essentially marked with little chemical marks. Okay, it's not changing your DNA, it's not changing your sequences, but there are little chemical marks being put on your DNA in each cell, and those marks are actually instructions for the cell to use that part of the DNA. That is the epigenome, right? Is those little marks being left behind to tell the DNA to be used for a given response to a given thing. In this case, it's an infection. And then antibodies are made by that cell, for example, to protect against that infection, because all of a sudden that part of the DNA was turned on. Okay. So I mean, that's a simplistic way of describing it, but it's essentially what's happening. And what's great about those marks is they stick around for decades. Also, what's great about them is that they're pretty universal across people. So, there is some variability between people, and we're seeing that in our program. But what's really powerful is that this technology has not been utilized for infectious disease, but it's been utilized for cancer, and it is actually doing very well for diagnosing cancer, because your body's also responding to cancer. And you can use that same epigenetic mark to identify the presence of cancer in people, or you can even use the epigenetic marks to look at cancer cells themselves to figure out what type of cancer you're dealing with. And it's a very robust product. And now there are companies that spun out of Stanford and other places that have been bought by larger companies that are building these diagnostics. And so we decided to take that technology and drive it towards infectious disease, drive it towards exposure to toxic materials, or precursors to toxic materials, so we could identify when people are working on those things, and use that black box flight data recorder as a new diagnostic target, right? And so that was the excitement of this program. Was why had no one thought about this? And people, and honestly, some people had tried to do this in the past, but they didn't have the tools. And so this is where you talk about the knife edge between feasibility and innovation, right? And we got to a point in 2017 where, there were some researchers out of Salk Institute, Stanford, even Duke and Icahn School of Medicine. Those people had all had come out with innovations and developed methods, and they were the innovators that allowed us to start to explore the epigenome, immediately before 2017 in ways that we couldn't do before. So this made it feasible. All of a sudden, it was feasible to do, and so we said, all right, well, this is the time. This is the time to give it a shot, right? And at DARPA, we often look at technologies and or problems and say, well, no one's given us an innovation to make it possible, so we're not going to waste our time on that right now. We're going to wait for people to think of new ways to skin this cat. Well, this cat had a new knife to skin it, in a very bad analogy. And so we had a new way to look at this problem and a new set of tools, many tools to solve it. And what we're finding is just absolutely mind-blowing. I mean, we are now a couple of things that are big. We can look at single cells and see how individual cells in your body. So instead of collecting a bunch of blood cells and sequencing everything in that mixture, right? We're going cell by cell. And we're sequencing everything in each cell that's associated with an epigenetic change. Okay. And so essentially imagine like treating each cell as an individual and then putting them in populations. And we're finding dozens of cell types that are part of this response. But it turns out you can almost diagnose the disease that you have by the cell types that are responding to the infection, which is pretty amazing, right? So now all of a sudden I have subpopulations of cells that uniquely respond to different types of infections. So even before I look at the epigenome, I can already make pretty strong diagnostic conclusions about the cell types that are involved in a given infection response. But then when I put the layer of the epigenome on top of that, and I start saying, okay, which chemical marks are associated with this infection in these cell types, now I have an added level of specificity that no one has ever had before. And so now we're getting to the point where we're beating, off the shelf or, the current state of the art in terms of our accuracy. Oh, yeah. But what I think the real juice here, and the thing that we wanted to go after, was two things. Number one, go back to the Ebola story, right? In Ebola, you got to wait a few days before you can see virus shedding from the patient. And even in the case of COVID-19, it's several days. It might be 5 days. It's variable when we actually see virus available for diagnosis from that patient. But that patient might have been infected without symptoms, without detectable virus for several days, and could have had an opportunity to infect many other people. So what we're saying in the epigenome is that, well, the epigenetic changes, we're seeing them happen in the 24-hour time window, right? After exposure, right? So within 24 hours of exposure, we're seeing epigenetic changes Not yet in COVID-19. We haven't proven that in COVID-19, but we're seeing in other types of infections like influenza and others. And so there's very good reason to believe that in COVID-19 we'll see the same thing. So we are pushing towards a diagnostic that catches it earlier in people, so that we can pull them out of the threat, when the ability to infect other people, right, and not pose a threat to other parts of the population.
Sure.
So the sooner we can diagnose, the better. So that's one thing about the epigenome. The other thing about the epigenome is it lasts for decades, right? So we've seen so many examples of epigenetic changes due to things like smoking or arsenic exposure. And now we're seeing an HIV infection in our program that we can see people 20, 30 years after exposure still have a robust epigenetic signal. And then the last thing that the epigenome gives us is it does degrade over time at a fairly constant rate across individuals. So in the case of HIV, we've been able to show that with a very high level of confidence, we can tell somebody when they had their last acute HIV infection, right? So HIV is, it never goes away once you get infected, but you go into acute phases and you go into what we'll call latent phases of infection, where you don't have significant symptoms, but the virus ebbs and flows in terms of its level of expression in the body. And so when you have an acute phase, that's a really high level expression, high level of symptomology. We can target and put time windows on when that happened. And so what we're hoping to do is put a time window on when people were initially exposed or had their first symptoms for COVID-19. And we want to be able to say, okay, they were here when they were symptomatic. Who else was around them, right? Or what part of the country were they in? And does that associate with an outbreak? So that gives you epidemiological data to work with to start piecing together the progression of the disease. And that's a whole level of diagnostics that we haven't been able to have before with serology, or what we call PCR, which is the conventional way of detecting virus. And so, this whole host response picture becomes very exciting and very informative for sure. And that's really the genesis. That's what drove us to this program in the beginning.
It's really amazing, and I spend a lot of time on the show talking about sort of the themes of aging and longevity, and obviously there's this whole theme in the wider sort of business now about the so-called epigenetic clocks, not just in one cell, as you were saying, but how you can look at multiple tissues now and know if my liver is aging at a certain rate compared to my pancreas. Once again, I'm thinking sort of out here in the private sector of the possibilities beyond, and it's just an amazing example of how something developed in this one context could potentially blossom into so many different fields. Really, really cool. Going now a little downstream to even cooler things. Well, if there could be something more cool, but I used to work for GlaxoSmithKline, and a couple of years ago, they made about a $750 million investment in something known as electroceuticals. In essence, trying to get the drug out of the equation. If this drug is just affecting some signal, why don't we get rid of the drug and try to affect that signal with some physical stimuli such as electricity? You have developed a program at DARPA known as electrical prescriptions, with ultimately the goal of avoiding the traditional medical interventions that may have different side effects and off-target effects by delivering non-pharmacological treatments via what sounds very, very similar. To the extent that you could talk about this, could you give us a little overview of, in my mind, even if somebody's sick in Afghanistan, you can push a button on my computer one day and, cure their something, trauma, stress, whatever. Take us a little bit down this path as well, because this is really, really futuristic but mind-blowing stuff.
Yeah, a lot of this work goes back to work done by Kevin Tracy at the Feinstein Institute. It created a lot of inspiration for this program. And there was a program manager before me, Doug Weber, who actually created this program. So he went through the pain I described to you earlier of making a new program at DARPA.
Yep.
And often what happens is you reach your 5-year expiration date, and someone else comes in and takes over your program. And you keep your fingers crossed that they don't mess up, right? That they don't make a mistake or do things that would go against what you were hoping for. But actually, that's part of the beauty of the agency, is that it allows for someone else to come in with a different flavor or a different mindset and take your program and oftentimes take it to a new level, right? You may have had early initial goals, but this person's coming in with new knowledge from the outside, different experiences and different expertise. And oftentimes what happens is the program grows in a new way that makes it bigger. And so electriceuticals or electrics, the ELECTRX, right? So the electrical prescriptions program really took advantage of some of that early work that Kevin Tracy did and others. This kind of phenomenon of stimulating what we call the peripheral nervous system. That's all the nerves that come out of your brain that don't go through your spinal cord. Essentially, all of those nerves go to your organs, right? Directly. It's kind of like a direct communication to your organs. And this program was about being able to communicate with those nerves to achieve very specific end organ functions, right? And so the old classic way of communicating with nerves is you jam an electrode in the nerves and you give it a little bit of electricity, and then that triggers the nerve to fire, right? But that actually is it's a very crude way to interact with nerves, and we want to build, and in this program of electrics, we wanted to build more elegant interactions with the nerves, right? And so, now what we're seeing are teams from Minnesota, General Electric, they're interacting with the nerves with ultrasound. They're focusing ultrasound and using artificial intelligence to identify a specific nerve that they know is going to have an effect, and they're stimulating that nerve with focused ultrasound that's non-invasive, and it can be done at home, in fact. And in fact, we are doing a clinical study right now with a home use platform where the patient themselves is actually stimulating their own nerves with a small ultrasound machine. So it is very feasible that this could be an at-home therapy in the near future. And we're treating all kinds of different disorders, right? So we're now closing out a clinical study treating rheumatoid arthritis. So we're controlling host inflammation by interacting with essentially the nerves within the spleen. And that is regulating how much the person responds in an auto-inflammatory or autoimmune manner. And so you can actually downregulate someone's autoimmunity with ultrasound, non-invasive ultrasound. It's really impressive. And there was actually a pair of Nature papers published about a year ago, along with an article written up in JAMA, how this same non-invasive ultrasound could be directed at the spleen and downregulate immunity. But then you could also use the same parameters, the same energy levels, frequencies, et cetera, to stimulate the hepatic nerve. And General Electric did this work, where you could stimulate the hepatic nerve to actually allow somebody to control their own glucose levels in a type 2 diabetic situation. And that clinical trial will be starting up very soon, as we get through the outbreak. But there's, and then there's other applications where and what's interesting is, depending on what nerve you target for stimulation, you can achieve, like I just described, right? You can downregulate inflammation, or you can control glucose for a type 2 diabetic. So you have two kind of like completely different effects depending on what nerves you're targeting. Absolutely. And that's the power of this, is that we're getting pharmaceutical level impacts with very different nerve interactions, but using the same tools. And I think that's powerful. We're also working with there's a team doing a clinical study right now in Australia to treat irritable bowel disorder. And you've seen companies spawn from this idea. One company spawned from the Electrics program that is now using sacral nerve stimulation, which is there are sacral nerve implants already approved by the FDA. So you can actually implant these sacral nerve implants and stimulate the sacral nerve to control irritable bowel disorder. So again, depending on the nerve you target, the effect can be quite different, but still beneficial. So it's a very powerful program. we actually wanted to adapt this program to modulate immunity for infectious disease. And we're not there yet in the program. It wasn't in the original scope, but that's an example of someone coming in with a different perspective to a program like me and saying, hey, why don't we think about how we could attack infectious disease? So we hope that either within DARPA or beyond DARPA, that we start thinking about ways in which we can stimulate the peripheral nervous system to upregulate immunity or to maybe control the cytokine storm that's associated with some infections to improve outcomes. So it's a pretty exciting set of possibilities with this program.
Amazing listening to the sort of the connectivity to all, and especially the immune system, which is in recent days is sort of been seen everywhere. It's one of those things where you think we understood it so well, but it seems in many ways more complex than the brain. it's with all of these unique facets, especially when we now encounter these threats that our bodies have never seen before. So yeah, really, really amazing. One of the things I wanted to ask you about with regard to the programs that you've personally designed. Obviously on the show we've talked a lot about sort of the triad of artificial intelligence, machine learning, and deep learning, primarily for things like rational drug design or selecting certain patients for a clinical trial. You have this program called Taylor, teaching AI to leverage overlooked residuals, where it seems to focus on human performance optimization and how we can use AI to study and identify and characterize various different factors that enhance or decrease human performance. Could you briefly talk a little bit about sort of the thinking behind that? Because it seems a little bit separate from the infectious stuff. So really cool to hear about it.
Oh, sure. I mean, well, Taylor happened because I was actually developing and now have a program called Measuring Biological Aptitude, which is trying to understand the molecular systems that drive human performance, right? Okay. So it goes back to, it actually was my epigenetics program, taken to a whole new level. And what I was trying to do in that program, we're still trying to do, and I think we're seeing some early success here, is linking very specific human performance parameters to the biological pathways, starting from the epigenome, going all the way through gene expression and protein expression to drive a particular performance phenotype, right? Maybe it's your VO2 max. Maybe it's your ability to deal with complex situations in a military setting, right? In the heat of the moment, how do you react? Sure. And can we describe that from a molecular pathway? So it's almost like diagnosing performance. So treat performance as a disease and diagnose it with the host response. That's what measuring biological aptitude is in kind of a nutshell. And it was a way in which we could explore a very complex, multi-spectral picture of the host, apply it to human performance. But I think that the Measuring Biological Aptitude program one day will also bring tools to diagnosing regular infectious disease and other types of diseases too. So the idea was, I kind of got into an entirely new space in human performance, but from a diagnostic perspective, like people had not done before. And that caught the eye of a fellow program manager, Adam Russell. And he and I spent many, late evenings, late afternoons debating the idea of how we can move from the classic ways in which we explore human performance to building a more holistic picture of the individual, but also understanding how people work together in teams. And so he and I went in kind of two different directions, really tackling the same problem. I went in the direction of understanding the molecular pathways that drive performance. Adam went in a direction of trying to describe different aspects of human performance from what we'll call a counterfactual perspective. And so counterfactuals are, in a very simple way, there are ways in which you can look at an outcome, but look at all the what if scenarios that led to that outcome to figure out, were there other ways that you could have achieved the same outcome, or that, that were affected by variables that you didn't apply. So I like to think about it as kind of like, you know, there's a way of convergent evolution. You can always get to an evolutionary endpoint in nature, but different species achieve it in different ways, right? And so can we consider all the possibilities to getting to that human performance endpoint, and use artificial intelligence to kind of rapidly sift through all the different paths to that endpoint? And so this program, Taylor, is about using not only the conventional methods of artificial intelligence, but new methods of artificial intelligence to explore all of the pathways to a given performance phenotype, right? Or given performance outcome in groups. And so that program will actually allow us to think about ways in which we can govern, you know, groups or lead groups into a given desired performance state, or individuals into a given desired performance state. For example, if I want to perform better in archery, or let's say shooting, because that's more relevant to today's warfare, right? So if I want to perform better in target shooting, is there a way that I could use an artificial intelligence system to explore all the possible things that impact shooting, including sleep, including diet, including training and certain types of training? And could I have an AI or an artificial intelligence platform that I could say, hey, look, I'm not doing super, you know, extremely well in this type of activity for the military. What are some things I can try? And can you play through all the possible scenarios for me to figure out what's going to give me the most optimal outcome? And that's, in a sense, what Taylor is getting towards, right? Is first, let's look at populations of people who are in very real military performance situations. And so we're working with different cohorts across the military right now to get that data. Let's let artificial intelligence systems explore all the different pathways to success for the individuals and the teams. And then let's try to personalize and translate that to individuals and use that same kind of knowledge base that we've built to explore all the possible paths to success for a given individual as they're going through and developing themselves as a warfighter. And so that, in the end, is Taylor. I think it's opening up a Pandora's box, because essentially what we're doing is saying you have to consider all the possible outcomes and all the possible counterfactuals to what you see as reality. And no human mind can get themselves around it. We have to use AI to do it.
Sure.
But we don't want to use old-fashioned artificial intelligence, right? And so, you know, our director of the agency, when he came in as deputy director, he brought in a concept in essentially saying we need a third wave of artificial intelligence. We need something that's beyond the current artificial intelligence systems. And he built an entire initiative driving us towards third wave AI. Taylor is one of many programs that is developed to really take advantage of third wave AI. And so for me, I am, again, an inheritor of that program under Adam, because Adam Russell has left and moved on to his next phase. And he trusted me, right or wrong, to carry this program to its completion. I think we have about a year left, a little bit less than a year on the program. So it's been fascinating for me, because now I've gotten to know an entirely new community of researchers through his passing of the baton.
Along those lines, and coming back to you now, obviously you've been able to work with a wide range of fascinating people in government, in academia, in industry, collaborate and so forth. Are there specific mentors, influencers over the course of your career so far that you'd like to highlight at this point, that, you know, if it wasn't for them, Dr. Eric Van Giesen would be doing something different at this point? Anyone you want to specifically shout out to at this point in the show?
I mean, there are people that I want to shout out to. I mean, there's a lot of people, right? I mean, none of us, you and me, like there are so many people that shape us, you know, starting from birth, right? Our parents and our family. And I mean, obviously, I'd say most importantly, my grandmother, like on my mom's side, she when I was young, she took care of me while my mom worked. I was one of the those latchkey kids who didn't have a mom at home all the time. So she was kind of my my primary caregiver. And I probably, when I was 4 years old, I would ask her questions, and she couldn't. I think it was through exasperation because I was asking so many questions all the time, and through I guess wise guidance. She said, if you're curious, there's a wall of encyclopedias over there, and pretty much everything you're asking is in there. Do you want me to teach you how to find the answers? And that started the quest, right? And that's it made me realize that there are answers out there, and you have to go use a little energy to find them, but they're there. And so that was the beginning. I'd say another couple of people who are very influential, former DARPA program managers. There's a number of them, right? Sure. And I, without offending anyone in particular, I don't want to name names, but you know who you are. And but I still talk to these people as for guidance, and for not on specific programs, of course, but like just general ideas and general thoughts, and what they were thinking at the time when they were at DARPA and how to deal with certain situations. And these people is an alumni network of DARPA program managers out there. And then I'd say another person who was really influential, who gave me really my first shot in science when I was in my second year in college, was a guy named Barry Spargo. He is passed away now, but he ran a very, very productive laboratory group at the Navy Research Laboratory. And he gave me my first chance to work in a lab, and he was patient with me while I infected many cell cultures through bad technique. And he kept encouraging me to keep moving forward. He was working with a guy named Alan Rudolph, who went on to become a DARPA program manager. And so those two guys have had a huge impact on me moving forward. And then my advisor for my dissertation work, Tom Skalak. I mean, so there are a number of people who have really helped along the way, but all of us have that experience, right? And so I think that's really important. I'm glad you asked the question, because those people need to be recognized for what they've done.
Absolutely. And I appreciate you taking the time to highlight them. And obviously we can always go into everybody, but none of us do this on our own. But clearly you've had a wonderful mix there that have, the proof shows the amount that you've been able to do in this short period of time. It's just really amazing, fascinating stuff. And I take my hat off to you if I had one on.
It's never enough though, right? I mean, you always want to do more. And I think you follow the same path, right? I mean, I imagine your time at GSK, there were 1,000 other things you wanted to do, and you never had the time.
Absolutely. That's why I do this show now. I get to talk to the people that are doing it. So it makes me feel like I'm part of it. But for everybody that is going to be watching this on the ideaXme YouTube channel, or listening on the various podcast networks that the show will be live on, you've been listening to the amazing Dr. Eric Van Giesen, Program Manager in the Office of Biological Technologies at the Defense Advanced Research Project Agency, or DARPA, really doing amazing things to execute on their mission to do research and development that expands the frontiers of science and technology. Eric, thank you for taking the time to come on the show, doing what you do for all of us, keeping us safe, keeping our troops safe. And thank you, as we say, for moving the human story forward, that extra step. Really an amazing time, an amazing episode. And thank you again for taking the time out of your busy schedule to share your knowledge with us.
Thank you, Ira. This is great. Thank you for the opportunity.